Three key factors. By the way, when we design wireless networks, 500 kilometers per hour is not high for some applications. So I am working on an application where we are talking to the planes, and the planes go at sometimes 1,000 miles per hour, very high speed. So this is 500 is nothing, and for that you have to worry about, again, same thing, at that high speed, what can you do, right? So all these UAV, I shouldn't call UAV, but all the drone stuff or all the unmanned aircraft, they are going very high speed. Alright, so three key factors. So basically, when you want to increase bits, there are three ways you can do. One is spectrum. Just get more spectrum, more hertz. You will get it. Second thing is spectral efficiency. Get more bits per hertz. Right? And that's where we can innovate. And third is the cell sizes. Make the cells smaller so that you don't go very far. Right? And that is what is happening. Basically, all three are happening. So LTE Advanced needs more spectrum than LTE, more spectral efficiency, better coding techniques, and smaller cell sizes. And the smaller cell sizes also give you spectral efficiency. They are related, because if you have very large cell size, you can't get that spectral efficiency. Right? So those three. Everything that we will talk about will fall into this, mostly into spectral efficiency, because we are trying to get more bits through, and that also includes reducing the headers and efficiency and so on and so forth, right? So, okay. Bandwidth. So how do you get 100 megahertz? Well, not many bands have that much capability, 100 megahertz total. So what they do is they do carrier aggregation, which we saw before, I think somewhere in 11N, 11AC. You take many bands and you combine them together. That is called carrier aggregation. Okay? And so they do 5 carriers now, allowed now. So they take 5 bands of 20 megahertz each. LTE uses 20 megahertz. So there they use 5 times 20, 100. And they will go to 32. So by the time you get to 5G, they will be using the whole world, basically. 3.32 times 20 is 640 megahertz. Every band will be used up. And high UE power, U is the high throughput needed. And then if you really want a gigabit per second, you're not going to do it on your tiny phone. You're going to do it on a big computer. And so, because you will need all this power to get there. UE, everybody knows, is user equipment, right? Alright, spectral efficiency. Frequency reuse factor of 1. What does that mean? Anybody remembers the reuse factor? If you had a cluster of 7, what is your reuse factor? 1/7. Because you are using in each cell only 1/7 of the band that you bought. You bought from the government 100 megahertz, and you cannot use 100 megahertz in every cell. You use only 1/7 of it because there are 6 cells around it. Right? Here they are using frequency reuse factor of 1, means in every cell they are going to use that. Every cell, same frequency. High order MIMO. And then, of course, we are going to send you 8 streams on the same frequency, same time, 8 by 8 on the downlink and 4 by 4 on the uplink. Again, these are somewhat extreme numbers, because 8 by 8 on the downlink, what it says is that the UE will have how many antennas? To do 8 by 8 MIMO? How many antennas on the UE? Nobody knows? To do 8 by 8 MIMO, how many antennas do you need on the transmitter and how many on the receiver? 8 by 8 means you need 8 on the transmitter, 8 on the receiver, right? You can have 8 by 4, where 8 on the transmitter, 4 on the receiver. So 8 by 8 MIMO, you cannot do on your tiny phone. I mean, not today, at least tomorrow you will be. So the thing is, that is what it needs on the downlink, and 4 by 4 on the uplink. So you are transmitting 4 antennas, and they are receiving on 4. New MIMO techniques. So they have some new MIMO techniques that we will talk about. Inter-cell interference, coordination, and cancellation. We will talk about all of these. These are the new features that they have developed to increase the efficiency. And the cell sizes are multiple sizes, so they have relays like we saw before in 11s. We had the main access point and the relays. So we have those, and then we have something inside the home called home node E and B. E and B is the evolved node base station. So home E and B and relays. So all of these things, these are the techniques. So carrier aggregation. Carrier aggregation, basically whatever you got, we will take it. So if you have these 5, we can take 1, 2, 3, 4 and combine them as if they were 1 and 3 on the other side. So the number does not have to be the same on both sides. Okay, so this one shows downlink 4, uplink 3. And this is backward compatible with LTE single carrier. So if there is an LTE device here which does not understand multiple bands, we'll just go on the first band, or whatever is called the central band. So main carrier, it doesn't have to be first band. So we'll go on the main carrier, and then we'll ignore all other bands. So each band itself does not have to be 20 megahertz. It could be 1.4, 3, 5, 10, or 20. And these numbers, 5, 10, or 20 are clearly easy to understand because 10 is half of 20 and 5 is this. But then they don't have 2.5 and 1.25. They have 1.4 and 3. And these numbers came about the previous life allotments. So in 3G, when you got the allotment, sometimes you got 3 megahertz, sometimes you got 5 megahertz, sometimes you got 1.4 megahertz. So they just took those numbers and say, okay, we'll use it for LTE Advanced. So basically all of these are not in the same frequency band. Some might be in the GSM band, some might be in the 3G band, some might be in the 4G band, and you can combine all of that. So 1.4, 3, 5, and 10 and 20 megahertz, each band can be that much. But you can have maximum of 5, and if you have all of them at 20, then you get 100. Right? To get 100 megahertz, you need to have 5 times 20. Each component can be different width. So it doesn't matter really, they don't have to be, for example, so far we have seen in 11 AC, we had 2 times 20, or 2 times 40, or 2 times 80, the bands were kind of equal, and then we kept dividing by half. Here, this basically we announced what is the size of the width of the band, and so it could be anything. And the numbers of components in the downlink and uplink can be different, but the downlink is generally more than the uplink, because base station is generally more capable than the UE. Alright? Having said that, generally, because it's quite possible that you just bought this latest smartphone which is capable of 5 thing, and then you went to some worst country where they just had LTE with 1 carrier, so the downlink would be 1 and the uplink would be 4, you won't be able to use it. But when you are using it, uplink is always less than the downlink. Equal to is possibility too, so it doesn't have to be less, it could be less than or equal to. Right? Because if you got it, if suppose you have 5 and I have 5, there's no reason for us to use 4 and so on and so forth, right? So, and generally the uplink traffic is less. That's another thing. So uplink is not only difficult because the UE does not have big transmitters, it also doesn't have too much traffic. Right? We download more than we upload. So the need is more, capability is more in the downlink. So the components can be contiguous or non-contiguous. So contiguous means next to each other like this, or non-contiguous means far away from each other like those. Now I don't remember this, but I think in AC, all the charts we saw, they are contiguous. We saw 160, 280s and so on and so forth, right? So here they went one step ahead of that, and they said, we'll just tell you where they are, so you don't have to worry about whether they're next or not. And there could be different cell sizes too. So this one is a bigger power, and therefore has a bigger distance, bigger cell. This one is medium power, has a medium cell. This one is low power, has a lower cell size. Right? And why they are different power? Because every band comes with a power limit. Right? Every one, when government gives you, they say that 900 megahertz you cannot use more than this, 6.5, 5.8, whatever. They give you a power limit. So depending upon whichever is the highest. And second, okay, alright, there is more thing too. It's not just the power, it's also the wavelength. Some wavelengths go far, some wavelengths don't go that far. So that is not shown here. But if this was a small wavelength red, this will probably go far. Okay? And so given the power and the wavelength, you will figure out what is the cell size. And then the directionality, how much directional you are. Because if you are very directional, then it will go in one direction, otherwise everything go in the circle. So each component carrier has a serving cell, and the size of the different component carrier cells may differ. Okay, so you can see right there are 3 carriers and 3 cells. Phi, MAC and RLC, radio link control. Phi, MAC and radio control are all extended to handle varying number of components. So everything knows that, okay, I'm 5 mile Phi, I'm 3 mile Phi, I'm 2 mile Phi. Depending upon that, they will select the right modulation and everything else will change accordingly. Large buffer in RLC to accommodate large data rate. And because now we are going to get 1 gigabit per second, we need storage to store things which are coming out of order, are not able to go, and so on and so forth. The buffering goes up too. So all of this is handled correctly. So much about carrier aggregation.